a lot to do today. I switched to, actually, need to share my screen first to do that. Okay, we're back. So step 2 in dynamic programming today. Let's get rid of these notes here. There we go. And in this session, I would like to address what I believe is there are two groups of folks that I believe we have, which are those that are still struggling with understanding recursion in general, and then folks that already have a grasp of that, and I want to give some ideas of some common pitfalls, as well as more insight into recursion, even for the folks that are used to it. And then we'll go into another set of mock interviews. This time, I'd say the level of difficulty has been enhanced significantly from the last time. And so I want to leave you plenty of time to do that. But I also want to give those that might have been struggling on the set of problems that we had to do for the mock interviews on Tuesday, some more insight, a review of that material, and then perhaps the insight will help you address this next level of problems. And I'm hoping to get recursion at least to click for a few folks. So to start off with, let's just chat for a little bit about what is the difference between these two squiggles here, dp square bracket I and dp of I here, as written this way. And what do folks think when I say that loaded question? One is array access, the other is functional. Yeah, and so with respect to DP in this DP week, what do you think that means? Yeah, I like some of these answers coming in. And that is all, those all seem like different versions of what I was hoping would immediately pop out to folks, especially all the ramifications there in space versus time trade-off. That's kind of a nice, really packed phrase right there, even because it kind of encapsulates all the other stuff. And I love that, because you can always, computer science is often just about choosing space versus time trade-off. And DP is fun in that it kind of demonstrates that in a way, and also recursion with a function call versus caching, as you go, shows that. So people are right on board there. And before I move on from that, I want to ask one more question, which is, are there folks out there that still feel that the recursion that we did last class still doesn't make any sense, or still painful? And feel free to speak up and not to be shy if it's still not clicking for you. And then if it is painful, or if it is misunderstood, give me some, quick expression of like, what is what is it? Is it, I don't know where to start? Is it, how do you do that? Like, how did you jump to that thing? Or you know, if there's some idea there. Recursive is easy, nice. So some folks are already, you know, moved past that, and that's fine. Yeah, so sometimes some problems are tricky. The visualization part, okay. Okay, good. What kind of, what type, doing the DP matching? Okay, an agreement on that. Good, okay. Well, I feel like, it seems like to me that there are still these two groups, but I feel like the group that there's less of folks that are, although there's still a few, and it's totally expected that some folks are struggling with just even trying to get the recursion part. It seems like most people are in the more, a little bit more experience with the part. And so that's good. Hopefully every year it gets like that, where, you know, people are just understanding recursion more quickly. But let's try to give a few insights for the folks. Let's start off with, you know, those that are still struggling with this recursive step. And, you know, I really want to hone in on what I think, for me, allows people to move forward, which is to give sort of a framework or power tools, as I wrote in this slide, for if you're stuck, you can kind of just try to follow these steps. And sometimes as you just go through these steps, it unsticks you. And that's partly because these steps are at least helpful for folks to, you know, face the inductive step of recursion, or the place where you frame the problem finally in a way that's useful. And also, it just gets you moving. And so sometimes just by moving, you're not frozen, because oftentimes that frozen part, especially in interviews, is where, one, you're not getting points, and then also two, you're not actually able to solve it's very hard to just stay frozen and then solve the problem. So it's much better to just keep moving and solving things that you can't solve. So let's just quickly review some things from Tuesday, and just give me a chance to show these steps and how they apply to each one of these problems that we've already looked at, partly to allow me to re-explain some of the stuff, because again, if this is your first time coming at this and you solve problems, it doesn't hurt to see this again, and I'll see it in a new light. So we had this house robber problem that I had you guys do during the mock interviews. And now I want to apply these three steps that I've presented here, which I'm just going to call the inductive leap of faith, which is just some fun terminology that I'll show what it means again, but I described it last time. Then go and start with the easy stuff afterwards, and then keep it easy by guessing everything. The point is that this should never feel hard once you're following these steps. The only hard part is just framing the problem in that way that allows that to happen. The steps themselves should be somewhat rote and mechanical. So leap. So given this array, these house values, let's say 1, 2, 3, 1. And if you remember from the robber problem, I didn't waste screen real estate to show this again, but the rules of the game are you want to rob the maximum values of houses. This array, say, represents a street, and you can't have any two adjacent values of the array taken to be robbed. So what leap means is, first of all, just define some value anywhere in the array, f of I, and define what that means to be the max value that I have accumulated as a robber up and to including the house I is what f of I means. And I don't, what I'm calling this leaping is, I don't know how to solve that, but I feel that's something I want to solve. I feel like that is something that would allow me to solve this problem in a recursive way, or a way that will relate to sub-problems. And Sometimes you can state that right away. Sometimes you can't. Sometimes it's the creative part. So for now, let's just assume, okay, that's what I want. Then you go back, and step 2 is do easy stuff. So, okay, I've got that. So now in recursive language, this is called going to the base cases, but it's just what are the easiest things to get oftentimes. And it's, oh, well, let me go all the way back. If f of I means max2 up into including I, well, if I go to the 0th house, so only including the first one, that's really easy. I would just always take that value. Up until including 2 houses, okay, that also is kind of easy. I just choose the max between the 2. Okay, and you can quickly see, like, you don't have to do too many easy. You might look for a pattern. We discussed that in the last class. The third step is make all the guesses. And this is definitely the most important step in my mind of these 3, in that you say, okay, those were some easy things. Now let me go back, and this is where you're actually going to find or figure out that recursive solution. I go back to some arbitrary location I, or sometimes it's helpful to go to the endpoint. Like, let me just solve. But you go to one point where you can make a decision. In this case, I go to some arbitrary location I, and I say, well, what are the choices if I want the max value considering houses up into including I at that point? And I know everything beforehand, but I don't know something at this point. And you have to iterate what all the choices are. And in this case, the problem only has 2 choices. You can only either rob the house or you don't rob the house. And then in blue, I place, after you do the step of where you iterate all the choices, so oftentimes there's many more than 2 choices, but it's usually very small. There's only a small number of things you can do. You write them all down, and then you move to the next thing, which is, given those choices, what rules were stated in this problem that then force my hand? So if this choice was something like rob house I, well, I know I get the value I, I'm just reading off the problem statement at this point. I can get that value I, and then I can only add to it the best, whatever value I had gotten up until including I minus 2. Basically, I couldn't have robbed the adjacent one, but I could have taken anything before that. And I don't know what those are. I don't know necessarily that I robbed the second to last one. I just know that I get the max up until that. See, I'm reusing this F that I just assume exists. And the other choice is not to rob the house I, in which case I don't get the house I value. I just get whatever, and now I don't have to skip the previous one. I just get whatever up into including the previous one. And again, I don't know how. So those are the 3 phases. And then again, from the last class, you see, you'd have to prove that out. And after you write that down, see if that is the recursive function, see if it solves the problem. So oftentimes you might have to change. You go back to step 1 again and say, okay, well, max value considering houses didn't work for this one. Let me move the problem on. But you follow these 3 steps. Let's just do it for another example that we also did in the last class. And that was the edit distance problem, where we have the 2 words, W1 and W2, and your job was to edit the word 1, so that's W2. So let's see how it applies to the 3 steps. So leap, and this one, gets even harder to just jump to this. So you might have jumped to something else, but we'll say, for the case, in this case, we use our suffix, prefix, joint to match it's a double prefix and say, okay, well, I just want some function dpij, which is defined as the minimum edit distance, so solving the problem, the minimum cost, in order to convert W1 until I and W2 until J into W2 until J. And so 2, going back to the easy stuff, that typically means, okay, well, let's go back to DP00, which means up until the first letter, so not including the first letter even, and then not including the second letter. So it'll just be empty and empty. There's nothing to do. You have 2 empty strings. So that's 0, there's no cost. Okay, and what if there's just 1 character in W1? Well, you can only delete it. And if there's only 1 character in W2, okay, well, you have to insert something into W1 to get it. And there might be other base cases in this one. easy stuff. And in this case, there was a lot of easy stuff to grab, and we recognized the pattern right away. But 3, once again, the most important step for this recursion is to go back now to what we had defined, the up until I, up until j, and then just look at, if that is the case, say I was at ij, and I just need to make a decision at that point. What are all the possible decisions you could do? And this problem clearly states you only have 3, insert, delete, and replace. And there's kind of a 4th one, which is the replace. If the characters happen to be the same, there's no cost. And even though that step is easy, iterating out like, what are all my choices? It oftentimes, by doing it and writing it out and being explicit about it, it oftentimes then leads you to, well, then what would I write down? And so for 1, it is you pay a cost of the insert 1 plus whatever it was that you were able to match word 1 up until I and word 2 up until j minus 1, because you've inserted now to match j. So you take, you ignore now the current character of j, and you just look at whatever j was before that character with whatever current characters I have at I. And similarly for delete, you do it but the opposite, because you're deleting 1 from I, so now you don't, W1, so you don't care about I, and you just look at everything up until I minus 1 and j. Anyway, the main point is it's not to completely redo the work we did to show these solutions for this, but to show that it's these 3 steps that, you know, if you're still struggling to work on, think about it in terms of these 3 steps and then solving each one of them, especially the idea of making all the guesses becomes very important. So are there any questions that come up based on that? Yeah, that initial expression. So maybe this question was asked back when I was asking what was the hard stuff, but, you know, coming up with the initial expression, which I would state in terms of the terminology I presented here, would be, you know, how did I define in the leap step? Why did I choose what I chose there? And I think the answer is both, 1, to continue to practice these things, and you'll see that you'll just get a little bit better at guessing what is the definition that you want to be recursive. And by recursive, again, it just means definition that you want that will continue to repeat itself as you solve the bigger problem. And 2, in addition to practice and it becoming easier, it's okay to be wrong. So you start with something, start making some work on the problem with that, and oftentimes that will lead you to the better solution. And even if it doesn't, remember this is an interview, and so if someone is seeing you apply a very logical approach to solving this problem, they happen to have given you a hard one, you may still win a lot of points by getting some good work done on the problem, even if it was an incorrect assumption of what your recursion was. Now, of course, it's better to be correct, but the game is all about getting as much points as possible before the end of the interview. Okay, any other last confused with parameters DP and not sure. Right, okay, so that I'm glad I looked at that one. So that has to do with, that's very similar to understanding what the problem is you're solving. So for example, in this case, which is easier to show, the house robber, the question is about the blue stuff here, the rules. So the question was kind of geared towards, I don't actually understand how to solve f of I given previous information and how to step through that information correctly. Like, why was it I minus 2 in the first line and I minus 1 in the second line? Well, I think in this problem, it's a little easier to see that it's I minus 2 because you are not allowed to choose. So once you've grabbed that one house value, so for f of I, I've grabbed that one house value, now I'm not allowed to choose the adjacent. So it has to be based on the combination of what the problem description was and the particular thing I'm trying to solve and the particular information I have solved previously. f of I, namely the way I described f. If you describe f differently, it might end up in different, ways you're going to iterate through f to get n. And that's just the thing you're going to have. That's the thing you need to practice. That's the crux of everything, is the combination of choosing the right f. What does it mean? And then what does it mean as what will be the ramifications that you have to iterate through it to solve it? Okay, so let's keep moving. So the takeaway is keep practicing this. It does take a while to sink in, and even those that have now basic recursion sunk in, it might take a while to solve for every type of DB problem. But try to use this pattern. Even if you're skilled at it, this pattern might be helpful, especially the idea of guess all the things. Get to an iteration point and guess all the things. I find it very useful. And the key thing to look out for as you're trying certain definitions, induction steps that you think might work, but then might not, is look for repetitive computations. So then as you go back to do all the guesses and try to solve things, look to see if this solution still involves you computing something over and over again. So you compute it once, and then you compute it again for I minus 1, and then you compute it again for I minus 2. Okay, that means you still have, that's the whole point of DP, is to not do that as much as possible. So if you have that situation, go back to your inductive step to see if you can clean it up and make it more efficient. Okay, so let's switch gears and look at solving a particular problem here, the immutable range sum query. So the statement of this problem is, given an integer array, nums, find the sum of the elements between indices I and j inclusive, and where I is always less than or equal to j, so I isn't going to go over j, you're always going to get a valid range, basically. And the minimum range, it looks like, would be one number. So given the nums in the example, the sum of the range from the first index, which is, or the 0th, and the second is 1. So you would add -2 to 0 to 3, and you get 1. And note, you may assume that the array does not change, and there are many calls of some range function. Okay, so this has been an odd DP problem, and some might argue you can solve it different ways or whatever, but in this DP week, we're going to look at it as a DP problem. And so perhaps you look at it and say, okay, well, we've got -2, 0, 3, -5. We've got some range, so we're seeing an I and a J kind of thing here. So I'm thinking intervals, and I'm thinking, this is, if I'm going to match to the types of DP problems, this is looking for a segment of the array. So I have a 2D problem, basically. So then I say, okay, a 2D problem. I've been taught these DP tables, and that seems like something that's going to really help me visualize this right away. So I lay out a DP table. So this DP table, that I get the choice of how I want to lay it out. I just happen to put, because it's a interval, I'm assuming that this is best solved by looking at the interval between the array to find that range, I and j. I just repeat the array on the top, the columns, and the rows. So -2, 0, 3. So what that means is the diagonals, so that would be my base case, would mean I is equal to j. So this is the case where you're asked the sum at I equals to j, and so the sum would just be the value at that ith position in the array. And so you see, filling out the diagonals here, -2, 0, 3, -5. And then the next step, so let me add a little drawing here to this. So in the next step, what we're looking at, so as we go to our ij is 0 in this case, 1. So I'm looking at this cell here. J means, so I'm just assuming that the columns are describing your J, so the second number in the array that you want to sum until. And so it looks like I can build this recursion I'm building up by looking at the value of the diagonal And now I just have to add to that value the next number that I'm adding to it. So in this case, it's -2, 0, which would be -2. In this case, it is adding 3 to the previous sum, which is 0. And I'm specifically trying to do this in what might be a recursive way, using these previous numbers rather than just saying, I'm getting the sum of these two values. That's what the DP table is for, is so that you can look at previous computations, not necessarily just solving the values of this. Okay, so adding 3 to the previous sum, adding -5 to the previous sum is -2, adding 2 to the previous sum is -3, adding -1 to the previous sum of 2 is -1. Okay, so I'm liking this DP table that I have, so I keep going. Sounds like something that could be useful here. Okay, now I've gotten to the, in this step, this will be now adding 3 numbers. And you can see that in this DP table. This is a particular type of DP solution where you do the diagonal, then you do the next diagonal away from the main diagonal. So this would be the diagonal and the next diagonal away from it. This one, and then now we're at the next diagonal away, and this is going from sorry, not 0, but going from having 1 number to 2 numbers to 3 numbers in your sum. And so now we add 3 to our previous sum, which is -2. Okay, that's great, so that gives you 1. Now we add -5 to the previous sum, which is 3, which gives us -2. 2 to the previous sum, -2, 0, -1 to the previous sum, -3, -4. And things are working and that the numbers are kind of working out, but I already feel kind of strange about this, mainly because as I'm looking at this, I'm saying, okay, I'm adding 1 to -2 here, and I'm also now adding -2 to 3 here, but I sort of feel like that computation was already done. And you can kind of look at it and say, okay, in order to get this sum, I've got -2 plus 0 plus 3, 0 plus 3, and I already did that. So this is sort of the feeling that you should get when you feel like you've gone down a wrong path. Like you should say, okay, well, it feels like wasted computation. I've done that already. Now I'm doing it again. And that's perhaps because we posed the problem, although we posed it in a recursive way. And if we keep computing along, this will be solved and the table will be correct. Correctness isn't always the correctness of the solution itself doesn't mean you've solved the problem with DP correctly. There's a more efficient DP solution to this. So you go back and say, okay, well, it doesn't feel like a table, and if it's repeated computation, most likely that means you're actually a dimension off. So instead of an n square, you should be looking for a linear solution. With DP, that's often how it works. It'll be from linear to n squared to cubed, etc. And so in this case, we say, okay, well, what allows me to reuse that previous sum that I had before? So I have this array, -2, 0, 3, and I had previously already computed -2, 0, 3 to get one of those sums. And now I just want the sum from 0 to -5. And I want to use 0 and 3 to get to that next sum. So do folks have an idea about that? I'm sure some of you experienced folks have some ideas about what is the better way to cast this problem. Okay, so somebody has posited some difference of sums, and so and also specifically from 0, and so that is like a cum sum or cumulative sum, which seems like a possible approach for this. So what that means, what he's saying is take the sum, so take this sum, the purple, and then, so from here to here, and then subtract this sum, the orange, from the purple sum, and that gives you, it gives you part of, well, it gives you what you want if it's cumulative up until here. Okay, so what does that mean? So in this case, it might mean our dp, so we're asking for some solution S. So jump to the solution we want, which is Si of j, where I is the first number and j is the last number. And we want to know the sums up until that. So we can look at dp, so some other thing that we're solving. So in this case, it might not be reusing the sums of intervals, and instead it's just using the cumulative sum up until j. So that's what dp in this case means. So in this case, j would be up until and including this, and then I minus 1. So this is I, so this is this, so I minus 1, so cum sum up until there. So if you do the cum sum, so here on the bottom is the cum sum, -2, -2 plus 0 is -2, then take the cum sum of this plus just one more, 3, and you get 1, this plus that, -4. So take this cum sum, -4, and subtract away what you don't want from the rest of the cum sum, which is the first one. So it wouldn't be this one because you still want that value, but it's, so sorry, it's not this one because you still want that value, but you take away this one. And so -4 and minus -2 is -2, which would be the answer from here. So that was just, so I don't want to go through more of this example. The two things I want to point out about this are, one, the original point is that even as you get good at seeing the DP problem, you could be solving the wrong one. And so it's important to continue to be wary that just because things are being solved, look out for repetitive computation. Perhaps you've posed the problem in an inefficient way. The next one is, in this case, there's a transformation. So there's a DP thing, which is cum sum. And you might argue that's not even DP, that's the simplest DP. This recursion is just, all the recursion I've stated is that I'm going to get the cumulative sum up until including this position by just adding this value to the previous cum sum. So that's about as simple of a recursion as you can get. Still is a recursion though, and you're storing that and you're building it up from the base case and going along. And then you're going to store those values, the cum sum, but you're going to return, the actual value you want to return is this sum between here. And so you do a transformation. So that's often will always be present in a DP problem, typically, where you're DPing something else. So you're using your DP table or recursion to solve some useful thing like cum sum in this case, and then returning a sum between interval at the end of the function when somebody asks. Okay, so this leads us to thinking about, and I just wanted to show a couple cases real quick, have a little game of it for the next 5 minutes. Let's pick the DP type of the next couple of problems. And remember, these are the DP types that I've brought up before, suffix or prefix. So given some data array, sometimes you'll build up a DP solution by having solved it for the prefix of the array, subsequence, solving it for some subsequence of building up, suffix and prefix at the same time, or subtree. And so here we go. This first problem, given an array of numbers, find the contiguous subarray containing at least one number which has the largest sum and return its sum. So that's looking for the largest contiguous subarray. So just a quick vote on what subtype that is. Sure, I'll show that again. Suffix and prefix, subsequence, suffix and prefix, subtree. So kind of split decisions between suffix, prefix versus subsequence. Some people saying also just suffix. One thing I want to point out, it's almost always the case when suffix or prefix that it can be either suffix, or you can almost always flip the problem around, especially if recursion versus recursion plus memorization versus bottom up. So they're often the same. And in this particular one, it's more efficient to do it. And this was actually one of the warm-up ones, I believe, or maybe it was a previous mock interview. But it can be solved very efficiently with the suffix. Okay, another one. Given a binary tree and a sum, determine if the tree has a root to leaf path such that adding up all the values along the path equals the given sum. A leaf is a node with no children. So given the below binary tree, the sum is equal to 22. Is there a path, that's the question we want to answer, that will be the sum 22? And there happens to be a path 5, 4, 11, 2. And so you return true from the function. And so just to review again, your choices are suffix, prefix, subsequence, suffix and prefix, subtree. And I think, yes, I think that's correct. So also looking at tree, things like depth first search, outside of DP works well oftentimes for problems. So sometimes things can be done with DP or not. But in this case, a subtree problem type would be useful, which is also like depth first search. So you could see it as a DP problem. And so sometimes tree solutions and DP solutions. In fact, the root of DP partly comes from graphs. Okay, final one, a bit harder. Given an input string S and a pattern P, so this would be like a regex pattern P, implement regular expression matching with the support for dot and star. Dot means match any single character, star means matches 0 or more of the preceding elements. The matching should cover the entire input string, not partial. So basically what you want is that the pattern matches the entire string. So it's not a partial match to it, like the first half of the letters or something, or finding some subsequent. And some of the special notes aren't really necessary for trying to figure out what type this is. So we have that pattern, and then we have this other string. So what do we think that the DP type might be in this case? Subsequence is an interesting choice. Also, there's some suffix and prefix. Prefix alone, that would be very impressive. So of the choices here, regex, you can see a lot as the edit distance problem that we solved previously, whereas instead of a word one, you have a pattern. And that can lead you to a solution that is suffix and suffix, or prefix and prefix, where you're kind of doing a very similar solution as the edit distance. And it doesn't hurt, as a closing note to looking at these types, that edit distance problem that we went through, you can try to pattern match it to a lot of other string problems that we'll see we'll have that flavor of matching something or manipulating a string, like trying to find the longest something within the string. So in this case, prefix and prefix work well. Okay, so 40 minutes in, that's exactly where I wanted to be as we get to our mock interviews, because these problems are a little bit harder, and I would like to give about 35 minutes, let's say. Let's go until 20 minutes before the end of class, maybe 15 minutes before the end of class. Maybe we will give 40 minutes actually per person on this one. That way you can read through it, I don't want you to feel rushed in this. Like oftentimes mock interviews, we want the time to be a little shorter and get you feeling in the pressure mode. In this case, because these are harder DP problems, this is our first week of DP, let's let you sit with it for a little bit more time reading through it, and then work through the problem though by yourself as if you're being interviewed. This is a mock interview situation, just with 40 minutes per person to do the thing. Well, actually, I think you need 35. Yeah, so something like that, 35, and then we'll split halfway through. We'll announce when the people should. We'll give you 5 minutes notice when you should be switching to the next problem. And just remember, if you're stuck, keep scoring points by using the tools we just discussed, and keep talking about what you are trying to solve after you've read through the problem, of course. So take your time to read through the problem. Okay, so let's break out into the rooms.
Rooms are open.
I just want to give a couple comments based on, I was able to assist in a couple rooms. And, oh, my camera's facing the wrong way. Hold on a second. Okay, there we go. So yeah, I was able to assist in a couple rooms, and what I would like to comment that I think can apply to everyone is, especially as the DP problems get more challenging, like the ones that we had today. The first thing is I highly recommend staying in the UMP section of Umpire, up until prototyping, until you are pretty confident that you have a solution that makes sense to you, both by solving the problem that we intended to solve, but also in a way that seemed at least somewhat computationally efficient based on DP. Jumping to the code, so in multiple situations I witnessed, sometimes the idea was, oh, well, I kind of feel like it might be close, so maybe if I go to the code, it'll clarify whether or not I'm there or not. The code will almost for sure not clarify whether or not you've prototyped it. Well, I think going back to the matching and trying to go back to prototyping, it's very rare that the code will, because code often just involves a lot of details that will actually just make it harder to see if you've solved the problem right. Although, as you do code, you will typically notice whether or not you're on the right track. If the code is very complicated, it often isn't the case, because DP, it usually is the case that if you've solved it in the golden path, if you come up with the right solution, the implementation itself will not be super complicated. So it'll kind of typically be a bit easier to code up. And then the other situation that I saw, the other thing I wanted to comment on was, so as you're working on the problem, so I saw a lot of, actually this happened every single time that in each one of the questions that I saw, people actually had some really good ideas that in my mind would lead to the best DP solution. But then because it was a bit more of a challenging problem, it takes more than one mind shift. Sometimes it takes another, you have a pretty good idea and you're on the right path, but they hit a wall. But really, the wall was just, so for example, just to make it a little more concrete, on the palindromic one, the palindrome, the longest subsequence, the wall was like, oh, I've got 2, but I don't see how going from 2 characters helps me go to 3 characters. Well, in that case, it's actually a 1 back, so that the 1 helps you with 3, and the 2 helps you with 4. And if you just continue with it a little bit and play with it and see that, you'll get past to the final stage where then you've solved the full recursion in the most simple way. So I guess part of my point is it's similar to the first point, which is to stick with, you're playing with the problem and you're close, you had some good ideas, but to keep playing with it in prototype stage before you move on to code, to make sure you've got the full solution and you can state it. Typically, once you've really solved it, you can state the DP problem in a few English phrases, basically. That makes a lot of sense. And if you can't, then continue to try. So I got a question here. And the time is over. So I'll respond to other questions. So I'll respond to this one and then any other questions you have. What are the good advice for switching top down and bottom up? Yeah, that's a great question because that actually applied to one of the rooms I was in. So in one of the rooms, they got closer to the solution by posing it as a recursive plus memorization. And you can always switch a problem from the top down to a bottom up. You can always take a recursion and turn it back into solving it using a table. In fact, a lot of times people don't even consider the recursion plus memorization a DP solution. Oftentimes, I consider DP also, but some people don't consider DP unless you're doing it bottom up, and that's partly because it's usually not as optimized if it's recursion. Like you are wasting call stack. Most languages don't handle that, etc. Anyway, so the first thing to know is you can always do it, and then the second is tips in terms of doing it. Well, I think one of the easiest ways to think about it is to go back to, so in a recursion, you always have to solve the base cases. So start with the base cases and then just try to get, one next step from the base case. And once you do that, it oftentimes gets you to think of the building up or the bottom up case rather than the top down. The other strategy I like to do to help me visualize bottom up versus top down, especially with 2D, is the DP table. So the DP table helps a lot. It really kind of forces you to think more about building up from some smaller cases, because what you're doing with the table is you're basically filling in the blanks. And the easiest way to fill in the blank is to fill it from information you already have. And so that's typically starts to lead you to the bottom up approach, because that's what that is the bottom up is you are propagating information from what you know to what you don't know yet. And then you'll take advantage of memory savings as you do that. Like you'll find certain ways to do that. Perhaps you only have to remember one row back or one column back, etc. Right, and so this suggestion, try to top down first. Try whichever one is easiest for. So it's a good idea, what he's saying, which is, hey, score points, which is the idea that we're always trying to get you to have, which is to score the most points. And if 1AA is just easier to think about, and you can, solve the hardest part of the DP, which is just understanding what the problem is and how not to repeat computation. If you do that with top down, bottom up, whatever, fine, do it. And then sometimes the interviewer, if you did a great job with bottom up even if it's the most efficient way to do it, for fun, just to see how you think, they might just say, well, can you do it recursively? And anyway, it's good to be able to go both ways, but typically they won't do that. It's more if you do it recursively, they'll ask you to do bottom up because it's typically not as efficient. Any other questions? Yeah, so I think just solve it the way that you're most comfortable. You can bring that up right away to show that you know the difference. That's a way to score points also, is to already bring it up while you're still thinking you don't know the solution. And that's fine. But be worried that then they'll suggest, okay, we'll do it this way. And maybe that's not the way you're comfortable with. So it may be better to, if you're more comfortable with one way versus the other, to do that first. Yeah. Cool. One more minute to see if there's another question. I don't think there's another question, so I just wanted to restate that I think at least all the rooms I was in, people were thinking really good ideas and very DP-like. And so I think even if you hit a wall with these problems, because these problems are not easy ones, I think everyone's doing really great. So be encouraged by that and go back and continue to play around with them. Maybe take a break for a little bit and then go back fresh and try to do it again with the knowledge that you are on the right track. Just push it a little bit more. And I promise you that with more practice, as you're doing this, even if you're only getting kind of close, you'll start to get it in the rhythm with it, and also stick with some of the harder ones and have those nailed as well. So great job. Practice with these problems, and pass the hacker rank. And next week we'll get into even more recursion with backtracking.